You ever felt confused by a confusion matrix? Not alone. Despite the name, it's supposed to bring clarity, not chaos. Today we're using a shade decision tree to predict sports fan behavior. But the real MVP of the model isn't just the tree, it's the confusion matrix that tells us how well the tree actually works. We'll unpack the whole process, how shade makes its decisions, what the tree shows us, and how to read every square of that famous 2x2 table, so you finally understand accuracy, precision, recall, and beyond. Let's make sense of the matrix. So what does Shade do? Think of Shade like a party planner using a series of group chats to figure out who's likely to come to the game. Instead of just asking yes or no questions like, are you free? And ask, is it the weekend? Is it a rivalry game? Is the weather nice? And it splits people into as many categories as needed based on how they answered. It uses chi-square tests to find the most meaningful differences and builds a tree of these interactions. It's like a game day flowchart for fan behavior. Let's start with the algorithm, Shade, which is short, or abridged for, chi-square automatic interaction detector, is a decision tree model that splits your data using chi-square tests. What makes it special is that it doesn't just do binary splits like CART does. It can split a node into 3, 4, even more branches if the stats say those groups are meaningfully different. So instead of yes or no, Shade can give you sunny, cloudy, and rainy, all as separate branches from the same node. It's like getting a more natural, human-readable flowchart from your data. So why is Shade good here? Imagine you're planning your stadium promotion strategy. You're not dealing with continuous numbers. You're working with categories. So team names, the weather type, the game day, whatnot. Shade handles that kind of data naturally. And because it allows multiple splits, like dividing weather into sunny, rainy, cloudy, it reads more like human decision-making, not a computer guessing game. It's like having a conversation with your data rather than interrogating it. Shade shines when you're working with categorical variables, like we're on our sports fan data set. Think about it. Rivalry game, day of the week, team. These are all naturally categorical. Shade helps us explore how these categories combine to influence behavior. It's also especially helpful when you need to explain your findings to others. Shade's trees are readable and intuitive, which is key when communicating insights outside of a technical team. Running our Shade model. So we gather our data, who the fan's team was, whether it was a weekend, rivalry status, last game result, weather. Then we ask the Shade algorithm, given all this, can we predict if someone attended? It goes step by step, finding the strongest variable first, splitting on that, then continuing down branches until it stops making mutable distinctions. It's like carving up a decision-making path with the sharpest possible knife, but only cutting when it stays. Then it makes sense. So once we prepped our data, picking the predictions in the target, we train the Shade model. In our case, we're predicting whether a fan attended a game or skipped a game. Shade goes through all the predictive variables, tests how strongly each one relates to the outcome using chi-square tests, and builds a tree from the most significant splits down to the least. To the Shade output. So the output's a tree. It's a hierarchy of decision rules. Each node shows the number of people in that group, what percentage attended versus skipped, and which category was predicted based on the majority. For example, node 1 says if it's a weekend and a rivalry game, 90% attended. So we predict attended. Simple, clear logic, backed by the data. It also comes with a risk score, which is considered the error of the predictions. But the real model performance comes from the classification table, also known as the confusion matrix. So how do we read a confusion matrix? So after we built our model, the next question is, how well did it do? So to answer that, we turn to the confusion matrix, a 2x2 table that compares our predictions with the actual outcomes. Think of it like this. If we get the predicted attended and actually attended, we have a true positive. But predicted skipped and actually attended, we have the false negative. But if we predicted attended and actually skipped, we have a false positive. And then predicted skipped and actually skipped, there's your true negative. So your true positives are we said they'd attend and they did. False positives, we said they'd attend but they skipped. True negatives, we said they'd skip and they did. And false negatives, we said they'd skip but they actually showed up. That's our foundation for all the model performance KPIs. The confusion matrix for our model. From your model, you'll get real numbers in each box of the matrix. Those raw counts feed into everything else we measured, so it's worth getting familiar with this table early on. Now to the KPI sheet. This is what each metric actually means. So let's break down the core metrics of each that come from this matrix. So first is accuracy. How often did the model get it right overall? So it suggests that the overall model performance across both classes. Then there's precision. Of all the times we predicted attended, how often were we right? It tells us how much we can trust a positive prediction. Then the sensitivity of everyone who actually attended. How many do we actually correctly catch? Specificity of everyone who skipped. How many did we correctly identify? Then the false positive rate. How often do we wrongly say someone would attend? So this is the likelihood of over predicting attendance. Then there's the false negative rate, which is how often do we wrongly say someone would skip. So this is likelihood of under predicting attendance. Then the F1 score is a balance between precision and recall. This is useful when you need both trust in predictions and in coverage. And then finally, support. How many people were in each actual class? This helps contextualize the metrics themselves. Now let's walk through each one. KPI 1, accuracy. So accuracy is the simplest one. True positive plus true negative over all the cases involved. So it's the overall percentage of correct predictions, but you need to be careful here. So in balanced data sets, accuracy can be really misleading. If most fans skipped, you could predict skip for everyone and still be 70% accurate. If most fans skip games, the model could just say skip every time and get high accuracy. So it's a good starting point, but it's not the full story. KPI 2, sensitivity or recall. This focuses on the attended group, so it's the true positive divided by the true positive plus the false negative. It tells you when a fan actually attended, how often do we predict it correctly? High sensitivity means we're good at catching real attenders. Low sensitivity means we're missing them. If this number's low, we're missing real attenders, like letting suspicious bags go through security. If it's high, we're catching what we're supposed to. Specificity. So this is the opposite of sensitivity. It focuses on the skipped group. So it's the true negative divided by the true negative plus the false positive. It tells us when someone skipped the game, how often did we correctly predict that? This is like the bouncer checking IDs. When someone shouldn't get in, did we actually stop them? Now to precision. Precision answers this. So it's the true positive divided by the true positive plus the false positive. So out of everyone we predicted would attend, how many actually did? High precision means we're not over predicting attendance. It's like a doctor diagnosing a disease. If precision is low, we're telling healthy people they're sick. Not ideal. High precision means we're not over predicting. Now to the F1 score. So this is a combo metric. The F1 score balances precision and recall. If you only care about one, the other might suffer, but F1 quickly checks them. The F1 score is like the Goldilocks metric, a balance between precision and recall. So F1 is 2 times the precision times recall divided by precision plus recall. If you have high recall but low precision, or vice versa, F1 tells you, nice try, but let's try to be more balanced. Think of it like a dating app that matches quality, precision, and quantity, recall. F1 says, don't just send a lot of matches or just perfect ones, do both decently well. It's great when you need both sensitivity and precision to be solid, like predicting who will show up to a game when there's limited seating. Now to the results of our model. So what's the big picture? Shade model gives us easy to understand decision rules. The confusion matrix gives us accountability. Did these rules actually work? And the KPIs help us pinpoint strengths and weaknesses in the model, whether it's great at detecting tenders, being conservative with predictions, or needs improvement in balancing errors. When you combine the logic of Che with the clarity of these performance metrics, you get a model that's not just accurate, it's also transparent. So what do we learn? Shade gives us more than just predictions. It gave us patterns we can understand and rules we can act on. The confusion matrix gave us our scoreboard, and KPIs like precision, recall, and F1 told us where we shine and where we need work. Whether you're a data analyst or just a curious strategist, remember this. It's not just about being accurate, it's about being insightful. And Shade gives us both. If this helped make the confusion matrix a little less confusing, go ahead and hit that subscribe button. I've got plenty more breakdowns coming your way, from modeling techniques to real-world data examples. So stick around, stay curious, and let's keep making sense of messy data together.